Hey folks, I got one last significant charge distribution to talk about as far as creating electric fields, and that's a line of charge if we're off center, okay? Meaning not off the edge, but somewhere else along the bar, okay? And this is probably the toughest one that we're going to do, well, except for the disk of charge. I think the disk of charge is the hardest one, but this is a second place one. So let's say you have a line of charge, all right? Now, before we get going on this, the electric field, let's say it's positively charged, it's going to look something like this, right? Assuming it's positively charged, it's going to look like that, okay? So what we're trying to do is figure out what that electric field is as a function of x and y, basically, or location. So I'm going to focus on a location like perhaps here somewhere. So there's going to be a component of the electric field that's perpendicular to the bar, and there's going to be a component of the electric field that's parallel to the bar. So we're going to have an E perpendicular and an E parallel, okay? Well, it turns out we have to find those separately. There's no easy way around it. You have to find each one separately with different intervals, okay? So let's set that up. So let's redraw the bar. I'm going to draw this nice and big because we're going to draw all over this thing. All right, so here's our bar of charge, okay? And let's put ourselves, I don't know, let's say about there. Okay, so not centered on the bar and not off the edge of the bar. And I'm going to give you some things to think about. So the perpendicular distance from that location to the bar, we're going to call that D, and that's a constant in our problem. We are going to measure everything from D. So for instance, going this way or that way, this would be a negative x, this would be a positive x. So x equals 0 at this spot, okay? Same with theta, okay, which I'll draw that in a second, okay? All right, so let's say that you have a DQ, and one of the things I like to do is look at the ends of the bar. So let's say there's a DQ right there. It's one of our little parts of the bar that's making an electric field. Okay, well that's going to make a field pointing this way. So I'll call that DE1. And there is theta 1, and that's going to be negative. Okay, and I'll show you in a second why. And by the way, because this angle here is 0, so we're going to say that's negative, and then going the other way will be positive. Let's say we have our final DQ way at the other end of the bar. Okay, so this would be our final radius, okay? And this would be, I'll call that theta 2, and that would be positive. And that's our final angle, okay? Now, what I am concerned with right now is just the component. I'll start with E perpendicular. So I'm only concerned with this component of the little electric field that each little DQ is making. I hope you'll agree that's equal to theta 1, and that component would be cosine, okay? So starting with our base equation, we've got electric field is K, the integral of dq over r squared r hat. That's our base equation. So a couple things we'll write in here. So electric field is K, the integral of dq over r squared. So the r hat part, we kind of decided what that's going to be. We want the perpendicular component of this, so we want cosine of the angle. Okay, so that takes care of your direction, your r hat. But now we've got three variables. We've got dq, we've got theta, and we've got r. And all three of those change as we move around the bar. Okay, well, let's start with the easy part of this. If you have a DQ, I'm going to look at the one over here on the far right. Its width will be dx, okay? And we know that lambda, okay, equals dq over dx. So dq equals lambda dx. And again, lambda would be the line charge density of the bar, like how many nanocoulombs per meter did you stick on the bar. So that would be something that would have to be given to you. You'd have to know the line charge density, okay? Now, so we can go ahead and plug this in for dq. Now, unfortunately, it doesn't really solve any of our problems yet because check this out. We're going to have a lambda dx in there. We're going to have an r squared down there. We still have that pesky cosine theta. So we have three things in there. We have three variables. And we have to get it down to one before we can integrate. Now, in a previous video, there was one example where dx equaled dr, or actually it was dl equals dr. In this case, that is not true, okay? So we cannot put a dr up here because we're not looking along the length of an r. We're looking along the length of the bar, okay? So they're not directly related to each other. So we have to get all this down into one variable. So we have to get everything in terms of x, of r, or of theta. Now, I'll go ahead and get rid of r first and put that in terms of x. So if I look at, let's say, this right triangle right here, okay, hopefully you would agree that it's a right triangle and that that particular radius at that moment, r, is equal to the square root of d squared plus x squared. It's a right triangle, okay? So I'm going to write that out for us. So little r squared is equal to d squared plus x squared. So I'm going to make that substitution in here, and that starts to help us with our issues. Okay, so we've got the integral of lambda dx over r squared would simply be d squared plus x squared, and then you've got your cosine theta. Okay, we're getting better now. Now we're down to two variables. We need to get down to one. We either need to get everything in terms of x or everything in terms of theta. Now, it turns out that you can do this either way, but frankly, one way is a lot easier than the other. It turns out that it's easier to get everything in terms of theta. Okay, so how do we do that? Well, let's look at this right triangle, okay, that we just drew. There are several relationships that I can write about the angle d and x and this r here, right? Again, I'll label that r just so we have it there. So I know that sine of the angle is equal to x over r. Okay. Oh, my pen fell asleep. There we go. X over r. I know cosine of the angle is d over r. Now, again, remember, r is equal to root d squared plus x squared. And tangent of the angle is x over d. You could use any of those, but it turns out that tangent is actually the easiest one to use, because if you use r, that's a problem because that's got x squared and d squared in it, and that's kind of a pain. So we're going to actually use tangent of theta, and I'm going to get x by itself. So x equals d tangent of the angle. So that will take care of this. For dx, we got to do a derivative. The derivative of tangent of theta is secant squared of theta d theta. Your calculus teachers would absolutely love this, that we're actually using this calculus to do a physics problem. All right, so now we've got dx and x in terms of theta. Let's make those substitutions. Okay, so we got k the integral of lambda times dx, which is d secant squared of theta d theta all over d squared plus x is equal to d tangent theta, and I have to square that, so it's d squared tangent squared of theta, and all that times cosine theta. All right, now we're going to make your trigonometry teachers very, very happy because we're going to use a trig identity here. All right. The numerator I'm going to leave as it is. So we got lambda times d secant squared theta d theta over. Well, here we can factor out a d squared, and you would get 1 plus tangent squared. Well, what's equivalent to 1 plus tangent squared? Secant squared. All right, and then you still have your cosine sitting out here. Hey, what happens to the secant squares? They cancel. Oh my gosh, thank goodness, right? Also, in addition, one of the d's cancels. Okay, let me make a little space here for us. Okay, so we end up with the following. we get E equals K, the integral. The D canceled, so that's gone, and you get a d theta up here, and down here you simply get a d, and then cosine of theta. Now we're getting somewhere. This equals k. Lambda's a constant, and d's a constant, so I'm going to pull those out, and what are we integrating? We're integrating cosine of theta d theta. Nothing could be easier. And you're going from theta 1 to theta 2. So you do theta 1 to theta 2. And you get the following. For the perpendicular component of the electric field, you get k times lambda over d. Okay, make sure that's a lambda there. Times, what's the integral of cosine? Well, it's sine of theta, evaluated from theta 1 to theta 2. And if you kind of tie this up a little bit, you get k lambda over d times quantity sine of theta 2 minus, oops, sorry about that, sine of theta 1. All right. Now, that's the perpendicular component of the electric field at this point. We also know that the field has a leftward component as well, which would be E parallel. So we have to go about and find E parallel. Now, I'm not going to redo all this, thank goodness, okay, because you don't have to. All right, what's the only difference for E parallel up here? What's the only difference? Let's start here. So that would be the same. What would change in this part of the equation? Well, it would simply be, instead of a cosine, it would be a sine. But it wouldn't actually be a sine. It would be a negative sign. Now, let me explain. Why is it a negative sign, Mashar? All right, well, here's why. When this angle's negative, we have a rightward electric field component. Our E parallel is to the right, is positive. If I do sine of a negative angle, I should get a negative answer, but I actually should have a positive DEX here, or DE parallel. Similarly, when my angle's positive right there, so like that DQ right there, that's making a leftward electric field. It's making a negative electric field, but my angle is positive and it's acute. So if I do sine of that angle, I'm going to get a positive number, but my electric field should be negative. So I'm going to replace the cosine here with a negative sign. Now here's the cool part. I don't have to rewrite any and all this stuff. All I have to do is get to right here, and the only difference is going to be, instead of a cosine sitting there, we're going to have a negative sign sitting there. So I'll start there. So E parallel would be k lambda over d, the integral from theta 1 to theta 2 of negative sine of theta d theta. What's the integral of negative sine? Cosine. So you get E parallel equals k lambda over d, and then you can go ahead and evaluate that too, and you get cosine of theta 2 minus cosine of theta 1. So that's your E parallel. Okay, so notice the only difference in the two equations is, instead of for the perpendicular it's sine, and for the parallel it's cosine. Now there are two more notes that I want to make about this. Okay, the first note is, let's look at E perpendicular. So E perpendicular if we're very far away from the bar. So as D gets much, much bigger than the length of the bar. Okay, so imagine that your bar, if we're really far away from the bar looks really, really small to us, right? So let's say here's the bar, and we are way over here somewhere, okay? Well, hopefully you would agree that if and I'll draw this a little bigger just so I can see it. So let's say this is D, and just for kicks, I'm going to put myself at the center of the bar, okay? So if I put myself at the center of the bar, here's 0. This would be X. We'll call that X1 to there. And this would be D. Okay. Hopefully you would agree with me that the radius from that to the far left of the bar is going to be really, really darn close to D. R is going to be roughly equal to D. Okay. So cosine of the, sine, that's our perpendicular, of the angle is going to be roughly x1 over d. Okay, so again, we have our little right triangle here. We have the opposite leg, which is our x1. And we're saying the hypotenuse is so darn close to d that we're just going to call it d. We're going to do an approximation. So if we look at our perpendicular equation, you get the following. You get k lambda over d, sine of theta 2, that would be x2 over d, okay, minus sine of theta 1, which would be x1 over d, okay? Well, you can simplify that a little bit, right? You got k lambda over d times x2 minus x1 over d. Well, first of all, I can combine the d's, make it d squared. And what is x2 minus x1? Well, that is simply the length of your bar. Okay, that's L. And so what do you get here? You get k lambda over d squared. X2 minus x1 is L. Well, what's lambda times L? Well, that's simply Q, the total charge of the bar. So you get what looks to be like a point charge. In other words, if you stand really far away from a bar, it's going to look like a point charge to us. So our equation gives us the equation for a point charge if you step very far away from the bar. Now, if you imagine the electric field goes like this, right? Okay, so it's going to kind of like that, and it's going to almost radiate outward. So if you're way out here somewhere, it's as if these lines are kind of just going outward like that. Matter of fact, they would kind of stop curving after a little bit. It would look like the electric field of a point charge. They would be radiating outward from a central point. What about E parallel right there? Well, as you can clearly see, E parallel is 0. There is no electric field parallel to the bar. Well, let's look at our equation. Okay, this is our equation for parallel. Well, hopefully you would agree there's theta 1 and there's theta 2, and theta 1 and theta 2 are really, really, really close to 0. So if I do cosine of roughly 0 minus cosine of roughly 0, I get cosine of roughly 0 is simply 1. So this becomes 1 minus 1, which, hello, is 0. So your E parallel is basically 0 if you're really far away from the bar, okay, and near its center. All right, so that was a long one, I know. I do have one or two more videos for you. The next one, I am going to show you using these results. I'm going to show you some shortcuts. So if you have multiple bars in a problem and they're asking you for the electric field at some point, I will kind of walk you through how to do that and kind of shortcut a little bit, make it simpler on yourself. And then the last video is about the motion of particles in the electric field. So I hope you found that video helpful and hopefully a little interesting, both on the physics level and on a mathematical level. And I'll see you on the next one.